Hi everyone. This PowerPoint slide is going to cover our lecture for chapter 13 on chemical kinetics. When we get into chemical kinetics, we think about two things, thermodynamics and kinetics. So what does thermodynamics do? We see if a reaction is actually taking place. And whereas in kinetics, we see how fast this reaction is taking place. By definition, the reaction rate is a change in the concentration of reactants or a product with time. And the units are capital M over S. So we have a reaction here, A going to create B. We see that A is completely converting to B, so we know that we're losing A and making B. Therefore, A is going to have a negative sign in front of it, whereas B is going to be positive because we're creating B. The rate equation for A would be negative delta brackets A, which is the concentration, over delta T, which is change in time. Whereas for B, it would be rate is equal to delta concentration of B over delta T, which is change in time. This image on the top is showing you how you're starting with one product, one reactant, and towards the end you are creating a product, but some of your reactant is still present. So when you look at time 0, we have all navy spheres, and if you look at time 60 seconds, most of the navy has converted to the red, but there's still some navy present. Understand that at some time in between the start and the end, there's going to be a time where the number of molecules of your starting material and the number of molecules you're producing are going to be at equilibrium. So for this reaction, A converting to B, we see on this graph here, the A is the black line and the B is the red line. You see your over time, over the 60 seconds, A is going from 40 to less than 10, and then B is going from 0 to somewhere around a little bit above 30. But you see it crossing an X right here. So that's where at somewhere maybe like 23 seconds, you have the same numbers of A molecules compared to the B molecules. So the rate for this reaction for A would be negative because we're losing A and we're creating B. B is going to be positive. Monitoring kinetics. We have a bromine solution here. You see in a picture where it's like a dark orange red color, and over time it's getting lighter, turning into yellow, and then turning clear liquid. Through this change of color, we see that the kinetic reaction is taking place. The left image here on the bottom shows that you need 393 nanometers of light to detect bromine absorption. And the graph here is showing you how the initial solution absorbs at a 400 nanometer, and over time it's going to decrease. So your T1 is the lowest, and then the T2 is a little bit higher, and then the T3 is the highest. So we have here a table, time versus bromine concentration, that is graphed. And from this graph we see that, so we are graphing concentration of bromine over time. And our time is going from 0 to 400 seconds. We see this curved line forming, and from that we can get the slope of the tangent line at any point, and with the slope we can find the reaction rate. The average rate equation for this bromine reaction, it would be negative delta concentration of Br2 over change of temperature, change of time. And in order to get the concentration change of bromine, we'll take the final and the initial difference. Here we have hydrogen peroxide reacting to create water and oxygen gas. This device you see in the picture is called a manometer, and it measures pressure changes. So we have our peroxide converting into a liquid and a gas. You see the liquid is collecting on the bottom of the flask, whereas the gas is floating around, and with the change of the gas you can see how much pressure you're increasing to. A common equation you've probably already seen is PV is equal to nRT, gas law. We rearranged this equation to get P alone. P is equal to N, which is your number of moles, over V, volume, times R is your constant, and T is your temperature. Remember to convert temperature to Kelvin. So for this reaction, we are putting the oxygen concentration because oxygen is the gas that's being created. So the concentration of oxygen is equal to 1 over RT times P. And then to get the rate equation, we just plug in from the slide before, delta of concentration of oxygen over delta T. And we know that concentration of oxygen is equal to this 1 over RT times P, so we just plug that in. So it's 1 over RT delta P over delta T. Next we have rates of reaction. We have this rate of reaction between bromine and formic acid at 25 degrees Celsius. So we plot the rate of the reaction versus the concentration of bromine, and we get this straight line. From the graph, we can try to find the slope of the line to get the rate constant K. But you guys see here for the rate constant, it's very similar. So we have 3.50 right here, 349, 350, 351, and then you got 348 here. So you just take the average of all, and that's where we get this one from, 3.50 times 10 to the negative 3 per second. Decomposition of peroxide. So the reaction kinetic can be studied by monitoring the pressure over time, which I already went over. And we can calculate the rate of the reaction by getting the slope of the tangent line. And we will multiply it by 1 over RT. Remember, R is a constant and T is your temperature. Reaction rates and stoichiometry. So now we have 2 moles of A, 2A approaching B. So we have 2 moles of A disappearing to create 1 mole of B. So our rate equation is going to be 1 over the number of moles. So for A, we're losing A, right? So it's going to be negative. And then we have 2 moles of A, so we will put 1 over 2. And then the same thing I went over. So it's delta concentration of A over delta T. And that will be equal to the concentration of B created, so delta concentration of B over delta T. This is a general equation here. So if we have lowercase a, which is a number of moles of A, plus the number of lowercase b is the number of moles of B, creating lowercase c, which is a number of moles of C, plus d, lowercase d is a number of moles of D created. Our rate of equation would be negative. So for A and B we're losing, and we're creating C and D. So A and B is going to be negative, C and D is going to be positive. So we would have 1 over the number of moles, so that's the lowercase a and b. So we have a negative 1 over A, that's this A, times change in concentration of A over change of time. And that is equal to the same thing for B, right? We're losing B because that's a reactant. Negative 1 over B times the concentration of B over concentration of time. And that is equal to now the creation of C. So we have a positive here. 1 over moles of C times the concentration difference over change in time. And the last one, very similar to C, is the D. So that is positive again, 1 over moles of D times change in concentration of D over change of time. Here's our first example. Write the rate expressions for the following reactions in terms of the disappearance of the reactants and the appearance of the products. I put this equation here for you so you don't have to go back to the slide before. So if you can maybe pause this video for a minute and try to solve this problem and then play it again to check if you are correct. Before you pause it, just a heads up. So here we have 1 mole of I, 1 mole of OCl, creating 1 of each. Whereas for B we have 4 moles here, we have 5 moles here, creating 4 and 6. Okay, so the answers are, for the first one, A, your rate is equal to negative, if I can go back. Okay, so we have our negative, so this is 1 over 1, so it gets cancelled out, and then you have your concentration I, and then you are doing B now for OCl minus, it's 1 over 1 again. And then for C, everything is 1 mole, so it's 1 over C, which is 1 over 1 times delta concentration of Cl minus over delta T, and that is equal to 1 over D, which is 1 moles again, delta OI minus over delta T. Whereas for B now, A here is going to be 4, and then delta concentration of NH3 And then we have here, you guys see negative 1 over 5, and that is the 5O2 here, the moles. And then we're creating C and D. And for C we have 4 moles, so it would be 1 over 4. And then for D, it would be 1 over 6. And that is here. And you put in the delta concentration of each section over delta T. Next example, consider the reaction 4NO2 gas plus O2 gas. You're creating 2 moles of N2O5. Suppose that at a particular moment during the reaction, molecular oxygen is reacting at a rate of 0.024 mole per second. At what rate is N2O5 being formed, and at what rate is NO2 reacting? Take a moment to pause this video and try to solve this problem. Okay, so you guys see that we have 4 moles, we have 1 here, and then we have 2 here. So we got our negative 1 over 4, creating negative 1 over 1, sorry, reactant, and this is our product, which is 1 over 2, delta N2O5. So we are given a rate of 0.024 for oxygen. So that is here. Our delta change in concentration over delta T is equal to negative 0.024, right? Because we're using up all the oxygen, so it's going to be negative. So we plug it in, right? We have our negative delta concentration of O2 over delta T is equal to our product, which is 1 over 2 delta concentration of N2O5 over delta T. So you rearrange this and you get delta times the concentration of N2O5 over delta T is equal to negative 2, right? So this 2 is becoming negative, times the negative 0.024 moles per second, and the 2 negatives gives you a positive, so we get 0.048 moles per second. So for part B, we have, remember we had 4 moles of NO2, so we have our negative, we're using this up, so it's going to be negative 1 over 4. And that is equal to our negative delta concentration of O2 over delta T. So we are rearranging this to solve. This 4 is coming to this side, and 2 negatives get a positive. So 4 times negative 0.024 moles per second gives you negative 0.096 moles per second. Next we have the rate law. By definition, expresses the relationship of the rate of a reaction to the rate constant and the concentrations of the reactants raised to some power. So we have here moles of A plus moles of B, creating moles of C plus moles of D. The rate would equal to K, which is a constant, times concentration of A to the power of X order, and then times concentration of B raised to the Y order. So overall, the reaction is X plus Y order. So for this example, we have a reaction taking place, 2 gases reacting to form another gas. The table here on the right is showing the data. So the concentration of F2 is increasing. The concentration of ClO2 is not increasing, so it goes up and then back down. But when we compare it, so we see that if we are doubling the F2, the rate is doubled. And then if you quadruple ClO2, the rate quadruples. So for this reaction, the rate would be K, which is a constant, times the concentration of F2 times the concentration of ClO2. Rate laws are always determined experimentally. The reaction order is always defined in terms of reactant, not product concentrations. And the order of a reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. So you guys see here for this example, right, if we put 2 in front of ClO2, this stoichiometric coefficient is not in the rate equation at all. So make sure that doesn't confuse you in any way. We have an example here. The reaction of nitric oxide with hydrogen at 1280 degrees Celsius is given. From the following data collected at this temperature, determine A, the rate law, B, the rate constant, and C, the rate of the reaction when the concentration of NO is equal to 12.0 times 10 to the negative 3 moles and the concentration of H2 is equal to 6.0 times 10 to the negative 3. So take a moment, try to solve this problem. Okay, so let's look at our equation here. We have 2 moles of NO plus 2 moles of H2 reacting to create 1 mole of N2 and 2 moles of H2O. So our rate would be K times the concentration of NO to the power of X order times the concentration of H2 to the power of the Y order. Once we know the orders of X and Y, we can calculate the constant K. And then we can calculate the rate at any concentrations of NO and H2. So for A, experiments 1 and 2 show that when we double the concentration of NO at constant concentrations of H2, the rate quadruples. So this is from the table. Taking the ratio of the rates from these two experiments, we have the rate of the second over the rate of the first. If you can refer back to the table, we see that the rate is about 4. And then your y power is getting cancelled out. They're both the same. So that is going to leave you at 10.0 over 5.0, and that would give you 2. So 2 to what power is going to give us that 4? And that would be 2 squared. So x is going to be equal to 2. So our reaction is going to be a second order in regards to NO. Then we look at experiments 2 and 3, indicating the doubling of concentration of H2 at constant NO. So we write the equation rate of 3 over rate of 2, and we see that 5 goes into 10 twice. And here the 10s are going to get cancelled out because we have constant NO concentration, and we see that for the H2 we get 2. So when you divide this, you get the 2. And 2 to the what power is going to equal to 2, and that would be 1. So our y is going to be equal to 1. So our reaction is going to be first order in regards to H2. So second order on the page before and first order for this. So our rate is going to equal K times the concentration of NO to the second order times the concentration of H2 to the first order. So overall, we would add the orders, so it would be 2 plus 1, and that would be a third order overall reaction. So now for part B, the rate of the constant K can be calculated using the data from any one of the experiments. So we rearrange our equation to get K alone. So we have our K is equal to the rate over concentration of NO to the second power times the concentration of H2 to the first power. So you just plug in from any of the experiments, right? And you get that K is equal to 2.5 times 10 squared. For part C, using the known rate constant and concentrations of NO and H2, we write our rate is equal to our rate constant, which we just calculated, 2.5 times 10 to the power of 2, times the concentration of NO, so that's 12.0, and that is to the second power. And for H2 is 6.0 times to the negative minus 3, and that is for the first power. And you multiply these together, you get 2.2 times 10 to the negative 4th. So first order reactions, we have A creating a product. The rate is very similar to the previous material, so we're losing A, right? So that's going to be negative, so rate is equal to negative change in concentration of A over time. The rate is going to equal to K, which is a constant, times the concentration of A. So you make these equal to one another, and you get this equation here. So delta A, bracket A, so that is the concentration of A at any time t, and A sub 0 is the concentration of A at time 0. So this is what you're starting with, and this could be at any time. So we have a graph here, natural log versus time. So at our starting point is here, and our slope is negative K, so that is our constant. So from the slope we can get K. The slope is negative because the line is going down. We have an example here. The conversion of cyclopropane to propane in the gas phase is a first order reaction with a rate constant of 6.7 times 10 to the negative 4 per second at 500 degrees Celsius. If the initial concentration of cyclopropane was 0.25 moles, what is the concentration after 8.8 minutes? How long in minutes will it take for the concentration of cyclopropane to decrease from 0.25 moles to 0.15 moles? And for C, how long in minutes will it take to convert 74% of the starting material? So take a minute, see if you can try to solve this problem. So, the relationship between the concentrations of a reactant at different times in a first order reaction is given by the equations that I just went over in the 2 slides before. So it would be the concentration of A sub 0 is equal to 0.25 moles, and that is at time 0, and at concentration of A sub T, that would be at 8.8 minutes. And in B, we are asked to calculate the time it takes for cyclopropane to decrease in concentration from 0.25 to 0.15. For C, no concentration values are given for C. However, if initially we have 100% of the compound and 74% of it has reacted, then we know to do the math by having 100 minus 74, which is equal to 26. So by math, you would write that concentration of A at time t over concentration of A sub 0, which is the beginning, is equal to 26 over 100. So let's go over the steps for A. So we need to convert minutes to seconds because our constant K has units of per second, or second to the power of -1. So we convert 8.8 minutes to seconds, so times 60 seconds per minute. The minutes are getting cancelled out. 8.8 times 60 gives you 528 seconds. So we write our equation, not ln of concentration of A sub T is equal to negative KT plus ln of concentration of A at sub 0, which is the beginning. So we plug in negative 6.7 times 10 to the negative 4th power times T, which is 528 seconds, plus ln of A sub 0, which is 0.25. And we get that equal to negative 1.74. So, because we have ln, we'll do the E. So concentration of A sub T, to get this alone, to get rid of the ln, we have to use E anti-log. So e to the power of negative 1.74 will give us 0.18. This is just algebra stuff, so if you don't recall this, take notes and try to see if you can recall it. For B, we're going to take ln of our end over starting, so 0.15 moles over 0.25 is equal to negative times 6.7 times 10 to the 4 times T. We're going to get T alone, and we get T is equal to 13 minutes. Where for C, now we had remember it said we use 74%, so we're using the 26% remaining out of the whole. So if you convert percent to decimals, 0.26, so you would divide it by 100. So 26 divided by 100 gives you 0.26. So ln of 0.26 divided by 1.0, which is a whole 100%, is equal to negative times 6.7 times 10 to the negative 4 per second times t. We get t alone, and we calculate t to be 2.0 times 10 to the third seconds, and we want to convert seconds to minutes, and that would be 33 minutes. Graphical determination of k. So our slope, which is noted by the letter m, is equal to change in y over change in x. So you pick any 2 points. The 2 points are picked out for us here, and we calculate the slope. So for delta y, we have, so it's x comma y on the graph. So these are your y values, and these are your x values. So we have delta y, which is negative 1.50 minus negative 0.34 over delta x. So that is 2430 minus the 400, and these are seconds. So we calculate it to be negative 5.7 times 10 to the negative 4 per second. M is equal to negative k, so the minus sign gets cancelled out, and k is equal to 5.7 times 10 to the negative 4th per second. We have an example here. The rate of decomposition of azomethane is studied by monitoring the partial pressure of the reactant as a function of time. The data obtained at 300 degrees Celsius are shown in the following table. Okay, so we see as time increases, partial pressure is decreasing. The question asks, are these values consistent with first order kinetics? If so, determine the rate constant. So take a minute to see if you can solve this problem. The strategy states, to test for first order kinetics, we consider the integral first order rate law that has a linear form. So that is the equation we used before too. So ln of concentration of A sub t is equal to negative kt plus ln of concentration of A sub 0. So if the reaction is first order, then a plot of natural log A concentration sub t versus t will produce a straight line with a slope equal to 2k. Note that the partial pressure of azomethane at any time is directly proportional to its concentration in moles per liter. Therefore, we substitute partial pressure for concentration, and we get natural log of P sub t is equal to negative kt plus natural log of P sub 0. So here, P sub 0 and P sub t are the partial pressures of azomethane at t is equal to 0 and at t is equal to any time. So we first construct the following table of t versus ln p sub t. And if you graph this, you will get a straight line. And by that, we can conclude that the reaction is first order. We can find a slope by taking any 2 points. For this one, we have 5.0 minus 5.05 minus 5.56 over 233 minus 33 seconds, and that gives you negative 2.55 times 10 to the negative third per second. So this is the graph. This is what it would look like if you were to graph that table. And you see how we have the straight line with the negative slope. Next we have first order reactions half-life. So that is T sub half. It is the time required for the concentration of the reactant to decrease to half of its initial concentration. So T sub half is equal to T when concentration of A is equal to half of its concentration. So it would be concentration of A sub 0, which is what you're starting with, divided by 2, which would get you the half. So you can do some math here and try to get rid of the natural log, and we get that the equation for half-life is equal to 0.693 over K. So we have an example here of half-life. For A, we see that after 1 minute we're going from 16 particles to 8 particles, and then at 2 minutes, so this is times 0, we have 16. At 1 minute we have 8, at 2 minutes we have 4, and at 3 minutes we have 2. So we're starting with 16, and our half-life is going to be the 1 minute, because the half of 16 is 8. It's not going to be like 2 minutes. You're not breaking the time in half. You're breaking the particles in half. So we have an example here. The decomposition of ethane to methyl radicals is a first order reaction with a rate constant of 5.36 times 10 to the negative fourth power per second at 700 degrees Celsius. The reaction is C2H6, and you're creating 2 moles of CH3. Calculate the half-life of the reaction in minutes. So you guys remember this equation here, 0.693 over K. We take that, so T sub half, right, for half-life. We use that equation, 0.693 over K. K is given to us here, 5.36. So we plug it in, and we are going to convert seconds to minutes, because the question states the answer to be in minutes. And we get that it is equal to 21.5 minutes. Next we have second order reactions. So these are going to be to the power of 2, indicating that it's a second order. So our equation now, so the rate is second order, so that's K times concentration of A to the second power. And we make the rates equal to one another, and we get this equation here. So for second order reactions, we get a positive slope with a straight line, and that indicates a second order reaction. Example here, iodine atoms combine to form molecular iodine in the gas phase. This reaction follows second order kinetics and has the high rate constant 7.0 times 10 to the 9th power at 20 degrees Celsius. If the initial concentration of I was 0.086 mole, calculate the concentration after 2 minutes. And then for B, calculate the half-life of the reaction if the initial concentration of iodine is 0.60 moles and if it is 0.42 moles. So take a minute to see if you can solve this problem. So the strategy we're using is the relationship, but for A is the relationship between the concentrations of reactant at different times, and it's given by the integrated rate law. So because this is a second order equation, a reaction, we use that equation I went over. For B, we are asked to calculate the half-life, and for the half-life we use the equation. So these are the equations you would be using. So the solution for A, we have 1 over concentration of A sub T is equal to KT plus 1 over concentration of A sub 0. So you plug it in the values, right? For A, it's asking at 2 minutes. 7.0 times 10 to the 9th given, 2 minutes given, we convert it to seconds, minutes cancels out, then seconds cancel out, and then this is also given to us right here, 0.086, and we get that concentration of A sub T is equal to 1.2 times 10 to the negative 12 mole. This is a very low concentration that is virtually undetectable. So states here that the very large rate constant that we had means that all of our I atoms combined after only 2 minutes of the reaction time. So for question B, we need to calculate the half-life. So we're going to go back to this equation here, right? For half-life, T sub half is equal to 1 over K times concentration of A at sub 0. So we will plug in everything. The concentration was given to us in the problem, 0.60 m. So when you plug it in, 1 over K is 7.0 times 10 to the 9 times the 0.60, we get 2.4 times 10 to the negative 10. And then for the second part of the problem where it says to do it for the 0.42, it's the same thing except this value is changing, and that is equal to 3.4 times 10 to the negative 10th second. Now we have our zero order reactions. So zero order is going to have a power of 0. And we make the rates equal, so we have our negative delta concentration of A over change of time is equal to the K constant times the concentration of A. So the line on our graph now has a negative slope, and the slope is equal to negative K. So for the half-life, the equation becomes T sub half is equal to concentration of A sub 0, so that's our starting, over 2K. K is your constant. Here's a summary of all zero order, first order, and second order reaction equations. We have our rate law, so you guys see everything is like going in a trend. Rate is, for first order, rate is equal to K. Second order, rate is equal to K times the concentration of A. And then the third order, rate is equal to K times concentration of A squared. So sorry, so this is your zero order, this is your first order, this is your second order. Next we have exothermic and endothermic reactions. Anytime you see an exothermic reaction, exothermic is going to give off heat, where endothermic is going to absorb heat. For the exothermic reaction, so it's going to give off heat, right? So as the reaction progresses, A and B react to form a high energy transition state. And the energy required to convert A and B to transition state is the activation energy for that reaction. By definition, activation energy is the minimum amount of energy required to initiate a chemical reaction. And for the endothermic reaction, you guys see the difference here for activation energy is larger as compared to the exothermic reaction. So for endothermic reaction, as the reaction progresses, A and B react to form a high energy transition state. So same thing repeating, the energy required to convert A and B to transition state is the activation energy for the reaction. So know that your activation energy for endothermic is going to be a lot larger than for exothermic, which is a smaller. Temperature dependence of the rate constant. So this is equation K is equal to A, which is your Arrhenius equation, times e to the power of negative activation energy over RT. So E sub A is the activation energy, units are joules per mole, R is the gas constant. Now it's not the 0.08, it's 8.314 because it's in joules. T is the absolute temperature, A is the frequency factor. So you can rearrange this equation and we can have natural log of K is equal to negative times the activation energy over R times T plus natural log of A. So we have an example here, the rate constants for the decomposition of acetaldehyde were measured at 5 different temperatures. The data are shown in the table. So plot natural log of K versus 1 over T and determine the activation energy in kilojoules per mole for the reaction. Note that the reaction is 3/2 order, and K has the units of 1 over moles to the power of half times second. So here's the values on the table format. So when you graph it, you're going to see that you have this negative slope. The slope is equal to this value here, so that is a negative activation energy over R, which is that's a rate constant. Here we have 1 over T, so we can get this value, and we can get this value from the graph, and we can calculate the activation energy from the slope. Okay, so this data given to us is in temperature, and we want to put it in 1 over T. So this table is showing you natural log of K values time over 1 over T, which is in Kelvin. So we can pick 2 points and calculate the slope. The 2 points here, you get the slope to be calculated to negative 2.09 times 10 to the 4th K, which is Kelvin. From excuse me. So we know that our slope is negative 2.09 times 10 to the 4, and that is our negative E sub A over R. We can plug in the value for R to calculate the activation energy. So you multiply R with this value, the negatives get cancelled out, so R is 8.314. And we multiply this, and the negatives get cancelled out, so our activation energy is going to be equal to 1.74 times 10 to the 5th joules per mole. The problem states to have the answer in kilojoules, so you can just convert joules to kilojoules by decreasing the power by 3. So it would be 1.74 times 10 to the 2nd power. There's an alternate form. These two equations you can also use. So if we have 2 temperatures, T1 and T2, then we'll use any of these. Natural log of K sub 1 over K sub 2 is equal to activation energy over R times 1 over T2 minus 1 over T1. And you can also use this equation. So for this example, the rate constant of the first order reaction is given 3.46 times 10 to the negative 2nd power per second at 298 Kelvin. What is the rate constant at 350 K if the activation energy of the reaction is 15.2 kilojoules per mole? So let me go back to this so you can try to figure it out. So 3.46 given to us, that's K1, T1, 298. Well, we're trying to figure out K2, and T2 is 350. So here, this is our 298 Kelvin, and we're trying to figure out the rate constant at 350. So we substitute everything into the equation, and we get K2 is equal to 0.702 per second. And we compare that to this K1, we see that our value is greater, obviously, which we expected, because at higher temperatures you would have higher rate constants. Next we have catalysts. By definition, a catalyst is a substance that increases the rate of a chemical reaction without itself being consumed. So what it does is it makes the reaction go forward faster, but none of it is actually being reacted. I don't know why it says too long description. I'll take this off before I submit it to you guys. So when you have a catalyst present, your activation energy is going to decrease and your reaction rate is going to increase. In heterogeneous catalysts, the reactants and the catalyst are in different phases. So here we have some examples: Haber synthesis of ammonia, Oswald process of the production of nitric acid, and catalytic converters. Whereas in homogeneous catalysts, the reactants and the catalyst are dispersed in a single phase, and they're usually liquid. Examples are acid and base catalysts. The Haber process here, so we have this plate, right, that our molecules are going to bond to, and once they bond to the plate, they'll react together to form some kind of molecules, and then they get released from this surface of plate, and that is the Haber process. So that's your catalyst, which is making the reaction faster. We also have enzyme catalysts. You've probably seen this in your bio class. When a substrate connects to an enzyme, it's like a lock and key model, and it will create some products that are going to be coming off of your enzyme. So having these enzymes is going to make the reaction go forward a lot faster. Another example here is the binding of glucose to hexokinase. So this little glucose is going to bind into this channel, right? So the glucose is going to enter through this channel, try to get into this space, and that's what you see here. Once the glucose is entered into that space, the geometry of the hexokinase is going to change, and it's going to close that open channel. We got 4 problems here. I didn't put any of the catalysts. I mean, there's no problems really to solve. I didn't go over any problems for that. So your homework problems are only 4 problems of the math that I went over. The rate loss, 0 order, first order, second order. If you guys have any questions, please feel free to email me, and I'll get back to you as soon as I can. Know that your homework is due Friday night. The answers will be available for you Saturday morning. That should give you enough time to get ready for the test, which will be out Sunday and is due Monday night. So that's the end of our lecture for chemical kinetics. Please feel free to email me if you have any questions. Try to solve these problems by yourself if you can. Also, if you need help with the algebra stuff, maybe you can look up a video of how to convert everything. In the meantime, I hope you guys have a great weekend, and I'll see you soon.